Hello. This will be a demonstration of proposition 23 from book 10 of Euclid's Elements, which says that a straight line commensurable with a medial straight line is itself another medial straight line. We're given two straight lines, the medial straight line A and the straight line B. And these two given straight lines, A and B, are commensurable with each other. And what we want to prove is that not only is A a medial straight line, as was given, but that the straight line commensurable with it, the straight line B, is itself also a medial straight line. Now, we'll begin by setting out a rational straight line, such as CD. And then we will construct two rectangles. The first is the rectangle contained by CD and ED. One of its containing sides will be the rational straight line that we set out, CD, and its other side, ED, will be such that the rectangle contained by it and the given straight line CD is equal to the square on A. We could find such a straight line as ED by use of proposition 611. This gives us a third proportional, which then we can use 617 to convert into a statement about the rectangle contained by the extremes being equal to the square on the mean. So here we would define ED to be such that CD is to A, just as A is to ED. Then 617, the rectangle contained by CD and ED would be equal to A squared. And then by actually making the rectangle, we would shoot a perpendicular by proposition 111. And then we would complete the rectangle by drawing parallel lines. So proposition 131. And then we could prove that this is a rectangle through means similar to book 2. But the point is, ED will be such that the rectangle contained by it and CD, which is this whole rectangle CE, is equal to A squared. Similarly, we will define the straight line DF to be such that the rectangle contained by it and CD is equal to B squared. And so we would do the same thing, shoot out a perpendicular, but first find the third proportional. By proposition 611, shoot out the perpendicular, proposition 111, draw some parallels, 132, prove that it's a rectangle in the method of book 2, and we're done. Okay. Long and short of that is that this rectangle CE is equal to A squared, and this rectangle CF is equal to B squared. Now, because A squared is a medial area, we know that it has to be a medial area because the straight line A was given as medial, and the square on a medial straight line is itself also medial. You can refer to proposition 1021, where we named medial straight lines. So because A squared is a medial area, and this straight line CD is a rational straight line, and an area equal to a medial area has been applied to the rational straight line CD. We know from proposition 1022 that the breadth of this rectangle, ED, is rational and commensurable with CD in square only. That is to say, it is incommensurable in length. So ED, by proposition 1022, because CE is a medial area and it has been applied to a rational straight line, the breadth of this rectangle ED is rational and incommensurable in length with CD. And because the two straight lines, A and B, are commensurable with each other, it follows that the squares on them are also commensurable. You could show this by use of proposition 10(9), that the squares on them must have a ratio of two square numbers. Because A and B are commensurable in length, we know from proposition 10(9) that the squares on them are in a ratio of two square numbers, but when two magnitudes are in a ratio of two numbers, they're commensurable by proposition 10(6), so that because the straight lines A and B are commensurable with each other, their squares are also commensurable. A squared is commensurable with B squared. So that because the rectangle EC was made to be equal to a squared, and likewise the rectangle CF was made to be equal to b squared in our first step, we can then say that the rectangle EC is commensurable with the rectangle CF simply by a property of magnitudes. 10, 12 if you wanted to be special, but just because the magnitudes here are equal, we don't necessarily have to use 10, 12. So the rectangle EC is commensurable with the rectangle CF because a squared is commensurable with b squared. But then the rectangle EC is to the rectangle CF just as the base ED is to the base DF. We know this from proposition 6(1). These are two parallelograms. The rectangles EC and CF are two parallelograms under the same height. So by proposition 6(1), they are to each other as their bases. The rectangle EC is to the rectangle CF, just as ED is to DF. So that because the rectangle EC is commensurable with the rectangle CF, it then follows by proposition 10(11) that the straight line ED is commensurable with the straight line DF. But remember that ED is a rational straight line incommensurable with CD, so that by proposition 10(13) and definition 10(3), we can say that DF is also rational by definition 10(3), but that it is incommensurable in length with CD by proposition 10(13). So that because CD is a rational straight line, it then follows that DF and CD are two rational straight lines commensurable in square only. Because they're incommensurable in length, but nonetheless rational, they have to be commensurable in square, and that only. The two straight lines, DF and CD, are rational straight lines commensurable in square only, so that the rectangle contained by them is a medial rectangle. This was the definition of a medial rectangle in proposition 10(21), where medial straight lines first arose. When a rectangle is contained by two rational straight lines commensurable in square only, it is a medial rectangle. And furthermore, the side of a square equal to that rectangle is itself also a medial straight line. But the straight line B is precisely that straight line, the square on which is equal to the medial rectangle CF, so that by proposition 10(21), the straight line B is medial. This is what we set out to prove, so we're done with the proposition, therefore, etc., QED. There's a porism appended to this proposition which tells us that an area commensurable with a medial area is itself also a medial area. This is proved in the course of steps 3 through 5, where EC is given as a medial area because it's equal to a medial square. And because the rectangle CF is commensurable with it, we were then able to prove that CF was itself a medial rectangle, and so this is where that porism would originate from. We would originate as a consequence of steps 3 through 5 in our proposition. What Euclid has done here is prove a kind of equivalency in the class of medial straight lines that we saw in the class of rational straight lines, or maybe not so much saw as defined. Remember that rational straight lines as a set of straight lines, as a class of straight lines, are such that any straight line commensurable with the rational straight line is itself a rational straight line, so that by commensurability, straight lines do not break out of the class of rational straight lines. What Euclid has shown in proposition 10(23) then is the same as is true of medial straight lines, that commensurability cannot break a straight line out of the set of medial straight lines, because when a straight line is commensurable with the medial straight line, it is also a medial straight line. It's contained in that same class of straight lines. And this is part of Euclid's project, not only of giving a taxonomy of irrational straight lines in discovering different classes and discovering different properties of those classes and differentiating the classes from each other, but also in ordering the irrational straight lines simply. that one can say that the class of medial straight lines, for example, is exactly as well ordered as the class of rational straight lines, precisely because it has this property that any straight line commensurable with the medial straight line is also a medial straight line. And so just as commensurability does not allow a straight line to break out of the set of rationals, neither does commensurability allow a straight line to break out of the class of medial straight lines. That's all I've got to say about this proposition, so I'll end the video here and move on to proposition 1024.